Every single day, Earth hurtles through a dangerous cosmic obstacle course. As our planet orbits the sun, it is pelted continuously by thousands of tons of unseen space rock flying in from all directions. The vast majority of this daily bombardment goes completely unnoticed. Tiny fragments hit our upper atmosphere and quickly vaporize, leaving behind nothing but a brief, harmless shooting star. But somewhere along the line, those rocks scale up. At a certain exact width, that harmless streak of light turns into a planetary catastrophe. The danger of an asteroid doesn't increase linearly, it scales exponentially. Because volume is tied to the cube of the radius, doubling the width of an asteroid results in an 8-fold increase in total mass and kinetic energy. Let's start with a rock measuring exactly 1 meter across. If an object this size hits the atmosphere, it creates a bright flash and a high-altitude pressure wave. It is essentially a cosmic firework. Expand that width to 50 meters, and the mechanics of the threat change entirely. At this mass, the rock encounters so much friction tearing through the sky that the sheer atmospheric pressure forces it to detonate mid-air, creating what is known as an airburst. We saw the result of a 50-meter airburst during the 1908 Tunguska event in Siberia. An explosion high in the atmosphere generated a massive shockwave that slammed into the ground below. Without ever carving a crater, that kinetic wall of air leveled 80 million trees across 800 square miles of forest. At the 50-meter scale, the primary weapon isn't the rock itself, but the massive kinetic energy it dumps directly into our atmosphere. Cross the 100-meter threshold, and the air can no longer stop the object's momentum. This marks the transition from mid-air explosions to direct kinetic ground strikes. If a rock this large hits a populated area, the collision displaces millions of tons of earth, carving out a crater several kilometers wide. This collision also generates a blast of thermal radiation. The sheer heat of the impact instantly ignites flammable materials for miles in every direction. Multiply that width by 10 to reach the 1-kilometer class. Because of exponential math, a 10-fold increase in width means a 1,000-fold increase in destructive energy. At this size, the impact creates an environmental collapse spreading across entire continents. The collision punches so deep into the crust that it lofts millions of tons of pulverized rock and dust into the stratosphere, physically blocking sunlight from reaching the surface. At the 1-kilometer scale, the immediate physical destruction of the crash is eventually eclipsed by the long-term starvation of the environment. Then there is the apex of the scale, the 10-kilometer asteroid. This is the magnitude of the rock that struck the Yucatan Peninsula and triggered the dinosaur extinction. When an object 10 kilometers wide hits at planetary speeds, the energy release is measured in millions of gigatons. The impact behaves more like a massive explosion than a collision, vaporizing thousands of cubic miles of the Earth's surface. The kinetic force is so massive that it causes the Earth's crust to oscillate like the surface of a pond. This structural distortion triggers magnitude 10 earthquakes and global tsunamis that reshape coastlines thousands of miles away. This culminates in a global nuclear winter. The planetary debris cloud remains in the atmosphere for years, halting photosynthesis and causing a systemic collapse of the global food chain. A 10-kilometer strike acts as a planetary reset button, indiscriminately ending entire epochs of life, regardless of how well a species has adapted. Looking at that exponential math, it is easy to feel fragile. We are moving targets on a rock flying through a debris field. But humanity has an advantage that the dinosaurs did not. We are the first species in the history of the planet capable of using physics to predict the paths of these objects and potentially prevent an impact. NASA and space agencies around the world maintain a 24/7 watch on the sky, actively tracking objects in the 100-meter to 10-kilometer range to ensure we spot massive threats long before they arrive. The cosmos is undeniably dangerous, but we have reached a point where math and surveillance provide us with a head start. Which level of the asteroid scale surprised you the most? Let me know in the comments below, and subscribe for more deep dives into the universe.